Good evening. Okay, I think we'll just start today's class with this join. So I thought like today we will discuss the assignment questions that has been given in your NPTEL that page. So this is the questions for the week one assignment session. So the first question is climate variables are statistical properties of weather data over periods of. Yes. Yeah. So in the first class, we had discussed like what is the difference between weather, climate, and what are the different climate variables that we use. And like when you are talking about climatology or climate of a particular variable, we generally consider minimum 30 years of data. The average 30 years of data for it to be considered as a climatology. So we have already discussed these things. So the answer is 30 years. Now the second question is which of these is not a climate variable? So 30-year average monsoon precipitation over India, maximum hourly precipitation rate in Mumbai. Yeah, good evening. Yeah, between 1990 to 2020, amount of rainfall recorded in an hour over Delhi on 30th July 2024, and the average yearly number of Category 3 hurricanes that have hit the eastern state of Orissa between 1980 to 2010. The question is which of this is a climate variable, which can be considered as a variable that we generally use for climate. So, which is actually not a variable. Which one is not? Amount of rainfall recorded an hour over Delhi on 30th July 2024. Third question is the biosphere affects the climate by affecting the atmospheric composition, trapping heat from the sun, changing the incoming energy flux from the sun, transporting heat from equator to the pole. So biosphere we know is basically the sphere where like all of us lives, including plants, animals, us humans, etc. So what exactly the biosphere do? Like how is it actually affecting the climate? Yeah. So biosphere is actually affecting the climate by affecting the atmospheric composition. Because as part of this anthropogenic activities, the human beings are emitting a large number of gases into the atmosphere, which is actually changing the atmospheric composition, especially the amount of greenhouse gases present in the atmosphere is actually changing. Yes, Ritu, you want to ask something? Your hand. Yeah. Yeah, so due to the anthropogenic emissions, actually, the amount of greenhouse gases that is present in the atmosphere is actually increasing. So as we know, like we have learned in the last class, like around 50% increase in the amount of carbon dioxide is actually seen due to enhanced anthropogenic emissions from the enhanced anthropogenic emissions. So it is actually increasing the amount of greenhouse gases present in the atmosphere. So that's how it is affecting the composition. Yeah. Yeah, that is basically driven by the ocean currents and everything. Ocean current, then there are atmospheric cycles and all. Hadley's. There are like through the atmosphere also they transport like through convection and oceans are also through atmosphere also there is actually. So mostly like this transportation is occurring by like ocean currents, and then we have like a lot of cells in the atmosphere known as Hadley, Ferrel, and Pollard cells. So what happens is like over the equator because of larger higher temperature, there will be a convection that will be happening in the equator, and this will be transported northward. And then once it reaches this higher latitudes, it will become colder, and it will sink over like at a higher latitude. And this thing again happens. Again, another convection cell is there in the atmosphere. So there are basically three cells, which is like Hadley, Ferrel, and Polar. Through these cells also we basically through the atmosphere we have transport of heat, and another way is through the ocean. These are the two major ways in which heat is actually being transported from the equator to the poles. Okay, I hope it is clear. Is it? So biosphere mostly affects us. So they are basically meaning like due to human activities or through some changes to the animal, some through animals or through like what plants or something, how it is basically affecting. The largest changes actually caused by us humans only, and that is by affecting the atmospheric composition by emitting large amount of greenhouse gases. The next question is global warming may be defined as. So they are telling like it is an increase in global precipitation. Then there is rise in concentration of carbon dioxide. Then there is rise in global temperature, and then rise in the concentration of ozone. When we talk about global warming, which particular variable we are actually looking at? Yeah. So it's basically the mean rise in global temperature. So yeah, again, the concentration of carbon dioxide, increase in the concentration of carbon dioxide is actually resulting in the rise in global temperature. So when we talk about global warming, we generally mean the rise in temperature. So as like it is actually a result of rise in carbon dioxide. So when we talk about this particular term like global warming is actually we are talking about the rise in global temperature, which is a consequence of the rise in carbon dioxide. So like you may get confused between B and C. The question is what is global warming? When we talk about this particular term, global warming, we mean the rise in temperature. And obviously, this is happening because of a rise in CO2. The rise in carbon dioxide is actually resulting in this, or this rise in temperature is actually a consequence of rise in carbon dioxide. But the global warming is a consequence of the rise in carbon dioxide. Okay. So the answer is C, not B. The region of the world that has seen the largest increase in mean temperature over the last 40 years. So we have been discussing like globally this much temperature has increased. Do you remember like what was that value? When we look at the global mean temperature, how much increase we are seeing actually in the last 200 years, 1850 to 2000, when we look at how many degrees of temperature actually we are seeing globally. Globally, do you remember the value? Like that graph and all. Yeah. I was asking like global mean temperature when you talk about how much is actually the increase in global mean temperature. We have been looking at the graph. Do you remember the value? Global mean temperature. Okay. Approximately 1.5 to 1.6 degrees Celsius increase was there when we looked at global mean temperature. Now this value of how much is actually increasing varies based on like over different regions we are getting different values. So the question is actually which region in the world is actually experiencing the largest increase in mean temperature over the last 40 years. So the polar region of the northern hemisphere, temperate region of the northern hemisphere, subtropical region of the northern hemisphere, and tropical region of the northern hemisphere. So these are the different options given. So when we look at the world, like different continents, when we look at North American region, which is generally having temperate climate. So over that region, we are having an increase of around 2 degrees Celsius, right? If you look at the graph, we are having an increase of around 1.9 to 2 degrees Celsius. And we have over the European region, we have an increase of around again close to 2 degrees Celsius increases there. So these are all temperate regions in the northern hemisphere. And then when we look at over Asia, again we have a value close to around 2 degrees Celsius. Now when we come to the southern hemisphere or like southern part, like in the South America, we have an increase of around like it is the value is less than 1 degree Celsius, and in the African region we have a value around close to 1 to 1.1 degree Celsius, and over Australia again we have a value close to 1 degree Celsius. So like on the temperate regions, if we consider like over North America and over Europe, which is temperate region, we have an increase of 2 degrees Celsius, which both are in the northern hemisphere only. And when we come a bit down, like over the Asian region, which can be considered as the tropics, there we have an increase of around 1.1 to 1.2 degrees. This is all no. This is also similarly around 2 degrees Celsius increase we have. But over the southern hemisphere, we have a bit lower increase. Like in the um, South American region, we have like around zero point 0.9 to 1 degree Celsius, and in the African region, we have close to 1 degree Celsius, and over Australia, we have again close to 1.1 degrees Celsius. So generally over the northern hemisphere, the values are a bit higher, but both temperate and tropics region are almost like having similar values. Southern hemisphere is having a little bit of lower increase in temperature. Now, when we look at the polar regions, like the Arctic and Antarctic regions, so Antarctic is part of the southern hemisphere. So, as you can see in the figure, this is the South Pole, and this is the Antarctic region. So, Antarctic is basically a landmass which is actually covered by an ice sheet. So, over Antarctica, we have an increase of around, so here if we look at, it is almost less than 1 degree Celsius temperature increase we have here. This is around 0.8 kind of. We have around 0.8 degree Celsius increase over Antarctic region, which is basically the south polar region. Now this is a North Pole region, which is the Arctic region. Now Now here if we look at, so Arctic, so Antarctic is basically landmass covered with ice sheet. And Arctic is actually ocean covered with ice sheet. So here the value is almost more than or almost close to 3. So this value will be around greater than 2.5. It will be like 2.6 or 2.7 degrees Celsius. So this is like almost double the global warming that actually we are experiencing. So why this is happening? So Arctic regions are, as I said, is basically ocean covered with ice sheet. So what happens when the ice sheet melts? Ice is basically having very high albedo. Ice are surfaces which has very high albedo. Albedo means like how much of the incoming solar radiation is being emitted by the surface. That is basically given by the albedo. So ice is having high albedo, which means it reflects most of the incoming solar radiation. So because of global warming, when the ice starts melting, what happens is that the darker ocean surfaces become exposed. And this absorbs a large amount of incoming solar radiation. Ocean surfaces, which are generally dark, has very low albedo value. So when the ice surfaces, which are having very high albedo, starts melting due to global warming, the darker ocean surfaces get exposed, which are actually having very low albedo values. And again, this will in turn increase more temperature. So this happens as a cycle. What happens is that due to global warming, ice sheets melt. This um, exposes the ocean, which absorbs large amount of solar radiation. Absorbs large amount of radiation, which will again in turn amplifies the increase in temperature or the global warming. So this happens as a positive loop or cycle. So because of this ice albedo effect or this particular loop, there is very large increase in temperature over the Arctic region. So Arctic is basically the polar northern hemispheric region. So because of the positive loop, so this cycle is basically another ice albedo feedback. Ice albedo feedback. And the process of this much amplified warming happening over the Arctic region is known as Arctic amplification. This particular phenomenon of the Arctic region experiencing almost double the warming compared to that of the global mean value is known as Arctic amplification. Arctic amplification. Okay. So if we go back to our question once again, what was the question? The region of the world that has seen the largest increase in mean temperature over the last 40 years. Now, can you again answer this question? What will be the answer? So, there is polar region of the northern hemisphere, temperate region of the northern hemisphere, subtropical region of the northern hemisphere, and tropical region of the northern hemisphere. Yes. Yes. Okay. Yeah, the answer is A actually, not B. Yes, Rutu, you want to ask something? No. Yeah. You are talking about the spatial map. Like this is actually a line plot. So like color map. Last class. Uh-huh. Yeah. So I think like the map that we actually discussed was just showing the temperature variability along the latitude side. So when we generally look at how the temperature is varying along the latitude, we will get like the tropical region are having the highest, and as we go up, the temperature will decrease. But when we actually talk about the warming, I don't think that is the. Let me just have a look at the figure that I showed in the last class. I forgot actually what exactly it was. Was I discussing the average temperature or was I discussing the warming? Yeah, that was actually the figure I think you're talking about. This particular So this particular figure you're talking about, is it? Yeah. So if this is basically the average temperature. If you look at the color bar, it just shows like how the average temperature is changing like globally. So average temperature in the sense like what is the general distribution pattern of temperature. So as we know, like equator basically receives like direct solar radiation, and as we go up, the solar radiation has to travel more distance to reach the surface of the earth. This is the general pattern that is seen over. This is how the temperature is distributed globally. So now we talk about global warming. What we actually talk about is how much increase in temp. So if you look at this region, equator region will be having an average temperature value. If you look at, suppose like as we were already telling, if you look at 30 years of temperature or the climatology of equator, we will be having, suppose I'm just giving you an example, suppose 35 degrees Celsius is the average climatological temperature over the equator. And if we go like a little bit higher in the altitudes, like the subtropical or temperate region, will be having a temperature of suppose 25 degrees Celsius. And in the polar regions, it will be around, it will be mostly negative. It is mostly negative. So let's assume like let it be minus 15 or minus 10 degrees Celsius is the temperature. So just like I'm just giving you example. So this is how the temperature is distributed generally. So when we talk about global warming, we are telling like in the last 200 years how much warming the region has been undergoing. So suppose in the last 100 years there have been a 2 degrees Celsius increase over the equatorial region. So here that increases 2 degrees Celsius, and here the increases let it be 2.1 degrees Celsius. But over this region, the temperature increases actually 3 degrees Celsius. So this increase is actually different, even though like this is the climatological temperature distribution pattern around the globe. But when we look at the temperature increase that each region have been experiencing in the last 100 or in this case it's 40 years, and the last few years, it is actually that amplification or the increase in temperature is actually more. Is that clear? Now, the next question is largest difference between summer and winter temperatures. So, So we have summer season and we have winter season, and we have like different regions, like we have tropics and we have subtropics and we have polar high latitude regions. So which region among these three is actually having the largest differences between summer and winter temperatures? Yes, the answer is actually continental interiors at high latitudes. Why is it happening? So two things. So here, like we have oceans, we have coastal regions, we have yeah. So oceans and coastal region will be having like kind of moderate temperature compared to that of the continental or land mass. Over the ocean region, the climate variability, this variability will be less compared to the land masses actually. And also compared to the interior regions, the coastal regions or the regions which are near to the ocean will be having less variability because the temperature of those regions will be highly moderated by the presence of the ocean, or we will receive mostly moderate climate in the coastal regions compared to the interior regions. The interior region will be experiencing very intense winters and summers compared to that of the coastal regions. So among these oceans, coastal and continental interior regions will be having the largest variability. That is one thing. And again we have equator, like the tropics, subtropics and the high latitude region. So among these three, the high latitudes will be having the largest difference because, so this is how the Earth is facing the sun during June. Generally, the period we have summer season, right? So during summer, the axial tilt or the axis is actually facing the sun. So the polar region is receiving like some amount of solar radiation. Okay. Now when December happens, what happens is that the axis which was tilting towards the sun is actually now. So if you look at the axial tilt, this is facing the sun. Okay. And some radiation is actually reaching the polar regions. Now during winter, the axis is actually facing away from the sun. So no amount of solar radiation is actually reaching the poles. Like these regions are mostly not even seeing sun during the, so it's like totally night zone. So the largest difference in the amount of solar radiation, in the amount of solar radiation received during summer and winter is for the high latitude regions. High latitude regions has the highest difference between the amount of solar radiation that it receives during summer and winter period. So we know like in the equator there isn't much change because it is receiving enough amount. There is very little change comparatively, that's what I'm saying. So the change is very less. As we go up actually, because of this axial orientation, one is facing towards the sun and one is facing away from the sun, the amount of solar radiation that is reaching the higher latitudes are keeping on decreasing. So because of that, the continental interiors at high latitudes will be having the largest differences between summer and winter temperatures. So summer and winter temperatures are basically driven by the amount of solar radiation that is reaching the region, that is particularly received over the region. So the large difference in the amount of solar radiation that is received during summer and winter is seen over the high latitudes region. And again, even in the high latitudes, compared to the ocean and coastal regions, the continental interiors will be having the largest differences. So C is the answer. Continental interiors at high latitudes. Now the next question: the mean lapse rate in the troposphere is highest in which of these latitudes? So if you guys remember, we discussed about like how the lapse rate is changing during day and night during how the we discussed how the tropopause height is changing over the equator and poles, and we also discussed how the latch rate is changing during different seasons. Like we told, like during the mean latch rate is in the troposphere is highest over the equator because of the largest temperature received over the region. Since the equator receives the largest amount of solar radiation, equator is the region where the mean latch rate is high. So latch rate changes based on season and also based on latitude. It also changes based on the time of the day. Now, climate determines the existing human adaptations in a geographic region. So when you the one thing that you have to keep in mind is that when we talk about climate, we are actually talking about like a long-term change actually. So like next 100 years, next 50 years, kind of like that. So like it is a long-term change we are talking about. Climate forecast generally talk about how the next 50 years or how the next 100 years are going to come, or like what we have to expect in the next 100 years or next 50 years is what climate tells you. It is just a long-term forecast. So that's one thing that you have to keep in mind. So the first question is true, as you said, how the human adaptations in a given geographic region changes as basically determine the climate of the region only. Now, climate forecasts can be used by farmers to determine when to sow crops in the next growing season. Is that true or false? The second one. And we talk about agriculture, like agrometeorology, a different branch itself is there. So does it actually matters at what? Do they have to look at the climate forecast? Sorry, it's climate forecast actually. That's what I was telling. When you talk about climate, it's always the long term. So is it true or false? Do you want to change your answer? So does it matter for a farmer like what will be the temperature in the next 20 years or next 30 years? Is it going to affect his crop, or is it going to change it during which season he is actually going to plant the crops or not? No, it doesn't, because the question is climate focused. So what actually matters for a farmer is actually the weather prediction. The short-term temperature or rainfall forecast is what actually helps the farmer rather than the climate forecast, right? He doesn't care like what is the temperature going to be the next. Like anyway, that is not going to affect his cropping pattern or cropping season. So this is false. Weather matters actually. What weather it will be, that actually matters. Weather forecasts help the farmers in deciding when to sow crops and all this. This is correct. When we talk about human adaptations, climate determines the existing human adaptation. Carbon dioxide concentrations in the atmosphere has increased significantly over the past 200 years. This is simple. No, very direct question. Yeah. Yes, it has increased. It has like almost doubled. Global warming is causing increased frequency of heat waves throughout the world. So we have been discussing about the increase in mean temperature, global mean temperature, right? So yeah. So the global warming, along with the mean values, it is also increasing the extremes. Global warming, along with increasing the mean temperature, It is also affecting the extreme, extremes as well. So heat wave is basically a temperature extreme. So generally it is generally like if the temperature is greater than 40 degrees Celsius for consecutively 2 days, the generally heat wave is declared. So this temperature threshold value, this value is for coastal or I think this is for coastal. So this value changes based on if you are considering plains, if we are considering coastal regions, or let me just confirm that the value is 40 degrees Celsius. So the value changes based on this is for plains. So 40 degrees Celsius, like if the temperature, the mean temperature, maximum temperature increases greater than 40 degrees Celsius. It is said that the region for more than for consecutively 2 days, then a heat wave is declared over the region. So it is basically periods of unusually high temperature over a particular region. From the normal, if there is a departure of from 4 to 6 degrees Celsius from the mean temperature, if there is minimum 4 to 6 degrees Celsius departure, then it is called as a heat wave. So I think 40 degrees Celsius is for plains, and coastal region has a bit lower temperature. Solar and volcanic activity can account for large part of global warming observed in today's world. Is it true or false? This is false. So are they actually part of climate change? What do you think? The solar and volcanic activity. So I get the answer. So this is false. So this is false. So as we were discussing, mostly we were discussing about anthropogenic climate change. Anthropogenic climate change. Anthropogenic in the sense it is mostly human induced or due to human activities this is happening. Is there something called natural climate change? What do you think? Like it is mostly a part of nature. Does something like that happen? Do you think like there is something called natural climate change? Or is it only anthropogenic climate change? Yeah. So what could be actually leading to natural? What are the natural activities or what are the things that is happening in the nature that is actually leading to climate change other than the anthropogenic climate change that we actually talked about? Do you know about any feature and which is a natural process that is actually leading to a climate change? Do you have any? Do you know like any process like that? Volcanic eruption, yeah. Yes, yes. So volcanic eruption, as you said, is one of the reasons which is causing a climate change. That is actually a natural. And second one is there is another important parameter also, which actually leads to climate change, which is when the radiation and the amount of radiation received by the radiation and the sun's radiation and the incoming solar radiation, the radiation that is received by it. So variation in the solar radiation. So how does a variation happens in the incoming solar radiation? The first one, so this is so we are discussing about three different parameters, which actually changes the amount of solar radiation that is reaching the surface of the Earth. The first one is known as eccentricity. So, what is the shape of the Earth's orbit around the Sun? Yeah. So, Earth is actually revolving in an elliptical orbit around the Sun. So, what happens is that the the shape of the orbit changes from circle to ellipse. So, this happens. So, there is something called eccentricity, which is basically the Earth's orbit, which is generally elliptical. Earth's orbit changing from being elliptical to nearly being circular. So the Earth's orbit is actually changing shape from elliptical to circular and then back to elliptical. So this is kind of a circle which is actually happening over a period of 100,000 years. So because of the large periodicity of this particular phenomenon, that's why we are actually not bothered about this. This is not going to affect in our lifetime. We are not able to see any major shift because of this. So the Earth's orbit is actually changing its shape from being elliptical to being nearly circular, and this particular phenomenon is known as eccentricity, and it is having a period of 100,000 years. The Earth's orbit from ellipse it becomes a circle, and then again becomes an ellipse. So the 100,000 years is the time that it takes to complete this cycle. So what happens when the eccentricity increases? Eccentricity increases means the orbit becomes more like close to of an ellipse, or it has a more elliptical shape. So what happens is that it actually changes the amount of solar radiation received between the closest and farther point from the Earth. So this dotted line is the actual elliptical orbit. So now we have a proper elliptical orbit. So in that case, this is the distance between the Sun and the Earth, and the Sun is at the farthest point between the when the Sun and the Earth is at the farthest point in its elliptical orbit, and this is its closest point. We have like perihelion, aphelion. Perihelion is the closest point, and aphelion is the farthest point, right? I said the other way around. I think perihelion is the closest point, and aphelion is the farthest point. Yeah, perihelion is the closest. This distance is known as the perihelion, and this is known as the aphelion. And the Sun is the farthest from the when the Earth is farthest from the Sun. So once it becomes elliptical, what happens is that the distance becomes equal. So the amount of solar radiation received when Earth is at the closest and farthest point kind of changes. So this basically determines the intensity of summers and winters. So that's what happens because of eccentricity or change in the shape of the Earth's orbit. Now the second one is known as wobbling. The first one is eccentricity. The second one is known as wobbling. What this wobbling means is that the Earth's axis is actually rotating. We know that the Earth is rotating around its axis, along its axis. On top of that, the axis itself is rotating, is actually kind of rotating on its own. Like as you can see, it is actually undergoing a circular motion like this, a cycle kind of like this. And this happens in every 11,000 So the axis which was initially here, after 11,000 years, it will, like half of, um, after 11,000 years it will be like this. Then with another 11,000 years, it will again come to the initial position. So to complete one cycle, it will take around 23,000 years. 11,000 is half of this. Okay, so the axis is also rotating on its own. So what happens because of this is that now the condition is like during January, the axis of the earth is actually pointing away from the sun. Okay. And during July, it is actually facing towards the sun. So that's why July we have summer and January we have winter. And now what happens if the after 11,000 years, what happens is that the direction of the axial tilt changes from like this to like this. Then during July, okay, the location will change actually. So during July, the Earth will be at this particular location, and during January, it will be like this. So yeah, that what happens due to wobbling. The rotation of the Earth's axis on its, that is the one more is there. I don't have the figure for that. Just a second. That is known as the axial tilt of the Earth actually changes from. So the axial tilt is around 23.5 degree north. So we know the axial tilt of Earth is around 23.5 degree north, right? This is Earth. This is the axis. This is the north. Like suppose it was like 90 degree. So this value is 23.5 degree, right? Now this third one is known as oblique. So this angle is actually changing from 22 degree to 24.5 degree. It actually changes from 22 degree to 24.5 degree. This is not a constant, it keeps on changing. And this basically happens in 41,000 years. This happens in 41,000 years. The axial tilt of the Earth actually changes from 22 degree to 24.5 degrees. Currently, the tilt value is 23.5 degree now. So, how much it is leaning towards the sun actually changes. So, when it is leaning more solar radiation will be received, and when it is leaning less, then the amount of solar radiation will reduce. So, the third one is obliquity. So, we learned three things. First one is the eccentricity, which is changing the shape of the Earth's orbit from elliptical to circular. This is actually having frequency of this happens. To complete one cycle, it takes 100,000 years, which means like during half of the period, it will change from a complete ellipse to a circle, and then again in another half of 100,000 years, it will become from circle back to ellipse. That is eccentricity. The second one is wobbling. Just change in the direction of the axial tilt of the change in the direction of the axial tilt. So this happens in every 23,000. Third one is oblique. obliquity means change in the axial tilt of the Earth. This changes from 22 degree to 24.5 degrees, and this happens in every 41,000. So this is also part of the natural climate change. So if you look at the values are like very large, right? So the amount of change in temperature that will be happening will be very slow, and this will happen like very gradually, right? And together these three things are called the Milankovitch cycle. These three things together is known as the Milankovitch cycle. Okay. Now, as you yeah, then there is like solar cycle is also there, like amount the number of sunspots in the surface of the sun, that also keeps on changing. So solar cycle is another component that actually um, lead to change in. So that is also another factor. So Milankovitch like solar cycle, and then we have this volcanic eruptions that we that which is already told. Due to volcanic eruptions also there will be climate. So yeah, what happens during volcanic eruptions is like that very fine particles of, why does volcanic eruptions lead to climate change? Volcanic eruptions actually lead to fine particles of large amount of fine particles of ash and dust being ejected. During volcanic eruption, large amount of fine particles of ash and dust will be ejected into the atmosphere, and a large amount of sulfur gases will also be emitted. What happens is that this sulfur gases combined with water vapor in the presence of sunlight and results in the formation of sulfuric acid particles. Sulfuric acid particles, which basically reflects the incoming solar radiation. And because of the energy at which the eruption occurs, these particles will reach the stratospheric height. So this will be mostly in the stratospheric region of the atmosphere. This will be mostly deposited in the stratosphere. So what is the issue if something goes to the stratosphere is that in the stratosphere the atmospheric stratified kind. So if you remember when we looked at the temperature profile, in the stratosphere the temperature was actually increasing with respect to height, which means the stratosphere is actually a stable layer of the atmosphere. No weather activities or no convection takes place there. So whatever is going into the stratosphere will have very high residence time. High residence time, which means it stays in the stratosphere for a very long period. So in the troposphere, what happens is that because of the surface is getting warming and the temperature is decreasing with respect to height, there will be like convective, there will be transfer of heat from the surface to the atmosphere constantly. The air parcels in the surface, warmer air parcel will start going up. As it goes up, it cools down. Then it will form clouds, precipitation, and all other activities are happening in the troposphere. So the particles that are actually in the troposphere also contains dust and other particles. But in the troposphere, due to the turbulent mixing and the convective activities that are happening, these particles will have very less residence time, which means like whatever goes into the atmosphere will come down and will be deposited in the surface in a week's time. So it won't stay permanently in the troposphere. But what happens in the stratosphere is that due to the stability or due to the stratification that is present in the stratosphere, whatever reaches the stratosphere will stay there for a very long period of time, that is for years. In the troposphere, it comes down within a week or a number of days, whereas in the stratosphere, it stays for number of years. So because of this, the sulfuric acid particles that are formed in the stratosphere stays there for many years. And as it reflects the incoming solar radiation, it reduces the temperature of the surface of the earth. Okay, so these kind of particles are the liquid or solid particles the tiny liquid or solid particles present in the atmosphere is known as aerosols. In the atmosphere, apart from the gases that we talked about, apart from the atmospheric gases, there are fine, there are like aerosol particles also, which is basically very tiny liquid or solid particles that is actually being emitted from the surface. So aerosols, not only through volcanic eruptions, aerosol reach the atmosphere through different processes like forest fire, natural processes like forest fire, through sea salt spray and etc. And through vehicular emissions, industrial activities also, aerosols reach the troposphere. But the aerosols present in the, so this aerosols has a general reflective property, or it generally has a tendency to reflect the amount of solar radiation that is reaching the surface of the earth. But when it is present in the troposphere, it is these aerosols kind of settles down in a week or in a number of days. But when these aerosols reach the stratospheric height, what happens is that it stays there for a large amount of time and then lead to like cooling the surface of the earth. So this is actually so if you can see the background figure, it came on top of where I wrote actually. So if you can see the background figure, this shows the this red region is the aerosol particles that reached the Earth's atmosphere due to a volcanic eruption that happened in 1991, which is the Mount Pinatubo in Philippines, erupted in June 1991, and a large amount of sulfur gases and other particles were ejected into the atmosphere. It reached the stratosphere and kind of spread over the whole globe. And that red region is actually, it kind of formed a haze kind of thing over that particular region. And this is the, I'll just copy paste the figure into a new slide so that you'll be able to see that. You are not able to see it here. So this is the amount of sulfuric acid particles that actually formed in the atmosphere. So it has formed kind of a haze in the atmosphere. And this is the temperature profile after 1991. During 1991, the volcano Mount Pinatubo erupts, and after the volcanic eruption, you can see like how much the temperature actually decreased. The temperature started going down from 1991 and it reached almost minus 0. From the mean value. So the 0 is actually the mean global temperature. From the mean value, it actually reached around minus 0.4 degrees Celsius. Like around that much the temperature decreased because of the volcanic eruption. So this is another factor that is which is natural, that is actually affecting climate change. Okay, so Milankovitch cycle is one where there is variations in the amount of solar radiation that is actually reaching the Earth's surface. And then the solar cycle is also there, um, which actually the amount of energy that is being emitted from the sun changes because of the yes, Ritu, you want to ask something? Yes, it will be there actually when we look at the like if we look at the global mean temperature, like the small dips we can see actually. Generally, this much decrease actually happened because this particular volcano emitted a large amount of sulfur gases. So the amount of it actually also depends on what exactly volcanic eruption which are actually rich in sulfur gases will have a higher impact. So Mount Pinatubo actually emitted a large amount of sulfur gas. So based on that variation, obviously these eruptions will have an impact on climate. So if you look at the figure, actually this is the decrease from 1991 to 1992. So when we are looking at the large profile, like over the 100 years or something, these things won't be that much clear because this is just a 1 year picture, no? So, but we will be able to see that variations, like a small dip and then an increase. So that dips we will be able to see due to volcanoes. Okay. This is not a like very regular phenomena, but yeah, volcanic eruptions are also happening. Yeah, I hope then it is clear. So we have solar cycles are there, then this Milankovitch cycle is there, then volcanic eruption is there, and also ocean currents. The changes in ocean currents also is another factor which is actually affecting this. Another natural factor that influences the climate change, apart from the anthropogenic climate change that we actually talked about. Yeah. Now, this we have already, the mean atmospheric surface temperature is around 15 degrees Celsius. True or false? We already calculated the surface temperature of the Earth, if you remember, from the amount of solar radiation that actually reaching the surface of the Earth and everything. We calculate. So, do you remember the equation that we used? So, we use the equation S by 4 into 1 minus alpha is equal to sigma t raised to 4. From this equation, we actually calculated the value of t. S is the solar constant. We derived the value for solar constant, and alpha is the average albedo, which was around 0.3. Sigma is the Stephen Boltzmann constant, which is having a value of 5.67 into 10 raised to minus 8. The watt meter raised to 4 Kelvin raised to minus. I think this is the unit. Yeah. And the value of solar constant was actually around 1370 watt per meter square. 1370, 1361 or 1370. 1361 watt per meter. So we actually calculated this atmospheric surface temperature. Okay. Most of so in this case we didn't consider the greenhouse gases. So when we use this equation, I think we got a value of around minus 15 degrees Celsius or something. So after including the greenhouse effect, we will get a value of around 15 degrees Celsius. I think the value that we got was around minus 50, which is because we didn't include the greenhouse gas effect. So once we include the greenhouse gas effect, we will be getting a value of around 15 degrees Celsius. Now, most of weather and climate relevant phenomena of the atmosphere happens in the mesosphere. So mesosphere is one of the top layers of the atmosphere. Does any weather or climate related phenomena happen in the mesosphere? Yeah, it is false because it is like least affected by It is the sphere which doesn't impact the climate, least affected by least influencing the climate. So the lapse rate is consistently positive over the entire height of the atmosphere. Is that correct? Atmosphere in the sense it includes troposphere, stratosphere, mesosphere and thermosphere. Is the lapse rate constant in the like all these layers, or if we take the entire height of the atmosphere, is it a constant? No, it is false. So how the lapse rate is changing within in different spheres, can you say? What is the value of lapse rate in the troposphere, or you can say the sign also. We have discussed the value also. Can you just say the sign? Sign is also fine. Is it positive or negative? The lapse rate value within the troposphere, is it positive or negative? Yeah, in the troposphere, the value is negative. The value is around minus 6.5 degrees Celsius per kilometer. And what about the sign of the lapse rate in the stratosphere? Is it positive or negative? Yes, positive. Then again, as we go up, now what is the third layer we have? Troposphere, stratosphere. Then we have mesosphere. How is the sign of the lapse rate over there? The mesosphere. Yes. In the mesosphere, again we have negative, and then the thermosphere we have positive. So it is like this. The troposphere, the temperature is decreasing as we go up, and we have the stratosphere where it is increasing. Then we have the mesosphere where it decreases. It reaches like the lowest temperature point in the Earth's atmosphere. It is around minus 80 degrees Celsius. It's at a height of around 80 kilometers. Then we have the thermosphere where the temperature again increases, right? So the lapse rate is consistently positive and the entire height of the atmosphere is false. Okay. So next I thought I'll just show the question. So next question is the molar mixing ratio of a gas component in a mixture is 0.15. If the molecular weight of the gas weight of the gas mixture is 20 gram per mole, the mass mixing ratio of the gas component is. So before going to this question, I thought like we will just discuss something known as the moisture parameters. So we know in the atmosphere, what is the concentration of nitrogen? Do you remember what was the concentration of nitrogen? It was around approximately composition of the atmosphere. So the atmosphere, we had around 78% of nitrogen and almost 20.9 or 20% of oxygen. And then the third most dominant element was the argon, which was around 0.9%, 2021. This is a rough figure, okay. Argon was around 0.9%. If you remember when we discussed about water vapor, the value of water vapor changes from 0 to 4% based on the availability of water vapor. Okay, it is not a constant. Suppose if we are taking an air parcel, a small component of air or a small volume element of the air. If it is dry, it means it will have 78% of M2, then 21% of O2, 0.9% of argon, etc. And when I am telling dry, it have 0% of water vapor. Okay. Now consider that I am taking a moist air parcel. So this is dry. Suppose I am taking a moist air parcel, then it will have 78% nitrogen. Okay, this uh, like kind of varies. Some amount of dry air, I will say. Some amount of dry air. Let's see, like in the parcel, maybe 83% of dry air, and then remaining 20% of moisture, 20% of water vapor. So when I talk about moisture, it has both dry as well as water vapor. But we generally, when we talk about dry air, it does like it has 0% of water vapor. So this value, like the amount of water vapor present in a particular air parcel, kind of varies depending on the location, depending on the time of the day, depending on the other atmospheric properties. So in order to represent how the in order to represent the amount of water vapor present in a particular air parcel, there have been a number of there are a number of parameters that we generally use in atmospheric science, which are known as moisture parameters. So moisture parameter generally tells you about how much water vapor is present in a given air parcel. So the first one that we use is known as mixing ratio. Mixing ratio can represent it using small r. Mixing ratio is given by mass of water vapor by mass of dry air. Suppose if we have 1 kilogram or 10 kg of dry air, within this 10 kg, how much kg of mass water vapor is present? Let it be like 0.1 kg. 0.1 kilogram per 0.1 by 10 or 0.01 kilogram per kilogram. That's much amount of water vapor is present. So mixing ratio basically gives you the mass of water vapor present in total mass of dry air. It is mv by mv. Now there is another component, another parameter, which is known as specific humidity. This is generally represented by the small letter q. This gives you the mass of water vapor plus the total mass of air. So this is the total mass of air that we are considering. So when we consider an air parcel, moist air parcel, it has dry air and it has dry water. So it has like mv amount of water vapor and md amount of dry. So the total mass of the parcel is mv by md, where mv and md are the respective components. So by total mass of the air parcel, that is specific humidity, mv by total mass of the air parcel. Now if we divide both numerator and denominator by md, we will get mv by md by mv by md plus 1. What is mv by md? It is nothing but the mixing ratio. So we can write r by 1 plus r. So specific humidity q in terms of mixing ratio, we can represent it using r by 1 plus r. Now there is another term which is known as relative humidity. This is so relative humidity basically given by mixing ratio by saturation mixing ratio. So I will just introduce into 100%. So what is saturation mixing ratio? Or what is basically saturation? So we know that when we consider an air parcel, it has a large amount of molecules within it, right? So this is dry air. Okay. It has large amount of molecules within it. It has some intermolecular space and everything. All these things are there when we are considering an air parcel, gaseous air parcel. Now, how does water vapor enter this particle? Water vapor enter this parcel through evaporation, condensation. In evaporation, when like moisture from the surface get evaporated, that's how like air parcel actually comes into picture. So the dry parcel becomes, so the dry parcel now became moist. At a given temperature, there will be some, there will be a particular amount of moisture or water vapor that an air parcel can hold. Suppose the temperature is 15 degrees Celsius. The maximum, so it already has dry air molecules. So we are adding water vapor in addition to the dry air, right? So it needs space to occupy. So suppose at 15 degrees Celsius, we can add 5 molecules of water vapor to the parcel. This is the maximum amount of water vapor molecules that the parcel can hold. So if we keep on adding, then the water vapor will start to condense because it exceeds the saturation limit. Now suppose at 20 degrees Celsius, 20 degrees Celsius the air parcel expands, so it has more space within the molecules, right? And the temperature increases, the air parcel expands. So that now there is more space. So at 20 degrees Celsius, maybe it can accommodate almost 8 molecules of water. These are just examples, okay? Don't take the numbers like. It's just for example I'm giving you so that you get a picture, like better picture. So saturation means that is the maximum amount of water vapor that a given air parcel at a given temperature can hold. So it actually changes based on temperature. So as the temperature increases, the amount of vapor molecules that the parcel can hold also increases. So it takes more time for the parcel to be saturated. Only once the parcel reaches saturation, the process of condensation, precipitation and all occurs. Condensation in the sense the water vapor molecule starts condensing and forming water molecules, and once the water molecules will start forming cloud particles. The cloud particles grows and finally become a rain droplet and then precipitates out of the parcel. So that's how the whole process of from vapor back to like surface kind of that cycle happens. So saturation is a very important term or a very important parameter that for the air parcel should reach before all these process starts. So saturation basically shows you the maximum amount of water vapor that a given air parcel at a given temperature can hold. Okay. So saturation mixing ratio is in the sense this MV will give you the maximum amount of water vapor that this particular dry air parcel can hold. So R is just actually how much is there, and RS gives you what is that maximum amount. So relative humidity is basically R by RS into 100 or specific humidity into 100 also. Like that also we can. Okay. So that is relative humidity. So we have mixing ratio, we have specific humidity, then we have relative humidity. So these are just terms which actually helps us to determine the amount of water vapor that is present in a given air mass. Now the question is the molar mixing ratio of a gas component in a mixture is 0.15. So let's molar mixing ratio means like in terms of mole we are telling how many amount of moles of this particular gas is present to the total amount of to the total amount of gas mixture. So Yi, let it be molar mixing ratio. Molar mixing ratio of gas component. 0.15 moles of this particular gas is present in the mixture that we are considering. And Mi is the molecular weight or molar mass, molecular weight of this particular gas, which is 20 gram per mole. Okay, and we have to find and the total mass of the gas mixture. M average is given by molecular mass of the molecular mass of the gas mixture is given by 20 gram per mole. So 0.5, so we can write the molecular weight of this particular gas will be 20 gram per 15 gram per mole. We need to find the mass mixing ratio of the gaseous component. Just give me a second. So mass mixing ratio, let it be Xi. Xi is equal to molar mixing ratio of the gaseous component into the molecular weight of the gas divided by the average weight of the gas mixture. So Xi is equal to Yi is given by 0.15 into molecular, the molecular weight of the particular gas is 50 divided by the total mass of the gaseous mixture is given by 20 grams. So the mass mixing ratio will be 0.15 into 50 divided by 20. Yeah, how much it is coming? What is the mass mixing ratio? How much it is coming? Can you tell me? Yeah. The answer will be 0.11 gram per. Now, this is, I think, from week 2. The environmental lab state in the troposphere. What is the lab state value in the troposphere? And what is the sign? The value is 6.5 Kelvin per kilometer, which means as we go up in the troposphere, for every 1 kilometer there will be a decrease of yes, and it is minus, indicating decrease. As we go up, there will be a decrease in the. Now, the atmospheric constituent responsible for half of the greenhouse effect. Which is that particular gas? Half of the greenhouse effect is B or C. Both answers. Only one answer. Yes. So even though we generally talk about carbon dioxide, like increase in carbon dioxide as a major part of the greenhouse effect, the strongest or the most potent greenhouse gas is actually water vapor, and this is also the abundant greenhouse gas. The most abundant greenhouse gas, which is responsible for half of the greenhouse effect. Okay, so but increase in water vapor, increase in water vapor doesn't actually lead to warming. It is not like if there is a like there is nothing like the amount of water vapor, like we say, like the amount of carbon dioxide has increased almost 50% in the last 100 years. There isn't such a large increase in the amount of water vapor that is present in the atmosphere, because the amount of water vapor that is present in the atmosphere will not increase beyond a particular point, because like if an air parcel has more water vapor than it can hold, or if it reaches the saturation point, then the condensation begins and the water vapor will eventually precipitate out. So the amount of water or water vapor which is present within the earth is always a constant. We can't add or remove the amount of water present. So what actually happens is that as due to global warming, increase in water vapor doesn't directly cause global warming. Directly cause global warming. What happens is that as the carbon dioxide and methane, which are like important greenhouse gases, increases, the temperature of the atmosphere increases. So as we discussed earlier, when the temperature increases, what happens to the water holding capacity of the atmosphere? When the temperature increases, the amount of water vapor that an air parcel can hold also, what will happen to that? The water holding capacity of the atmosphere we discussed when we discussed about saturation. What happens to the water holding capacity of an air parcel when the temperature increases? It increases or decreases? What happens to the saturation of the saturation level of the parcel when the temperature increases? Can you tell me what happens to the saturation? Yeah, saturation level also increase. So we can see the parcel will be able to hold more amount of water vapor. So as the yeah, exactly. So as the carbon dioxide and methane are increasing in the atmosphere, we know that the temperature is also increasing. Carbon dioxide and methane is increasing, temperature is also increasing. When temperature increases, the water holding capacity or the water vapor holding capacity of the atmosphere also increases. Water holding capacity of the atmosphere increases. So now more amount of water vapor is present in the atmosphere because it can accommodate more amount of water vapor. So the atmosphere is capable of holding more amount of water vapor because of the increase in temperature. So this will eventually lead to, so if more water vapor is present, it will again lead to more amount of temperature. So this is actually kind of working as a loop, like again a positive feedback loop. So this is a water vapor feedback. Earlier we learned about ice albedo feedback. This is water vapor feedback. As the temperature is increasing, the water holding capacity of the atmosphere is also increasing, which eventually is leading to more increase in temperature, and it is kind of happening like a cycle. So this is like water vapor feedback. Water holding capacity increases, then the amount of water vapor present in the atmosphere also increases. This will again lead to more increase in temperature. So this is acting kind of a positive feedback. So that's why, yeah, that's how water vapor increases the temperature of the atmosphere. So it doesn't actually generate or cause global warming. This is actually happening as a consequence of global warming. Water vapor is amplifying the existing global warming, through which it is actually being responsible for half of the greenhouse. No, it is already responsible for greenhouse effect, but it is actually taking part in global warming by this positive feedback loop. Yeah. So the next question, we have already solved similar question in the last class. We will do this one as well. So if the mean temperature of Jupiter's atmosphere is 165 Kelvin, molecular weight is 2.22 gram per mole, acceleration due to gravity. Question is not visible. Okay. Okay. Yeah, yeah. So I'm telling you the question. So the question is, if the mean temperature of Jupiter is 165 Kelvin, the molecular weight is 2.22 gram per mole, and the acceleration due to gravity is 24.8, then what is the scale height of the atmosphere? So they have given the parameters of Jupiter's atmosphere. The things that are given are the temperature of the surface temperature of the Jupiter's atmosphere is 165 Kelvin. Sorry, not surface, mean temperature is 165 Kelvin. Molecular weight is 2.22 gram per mole. Acceleration due to gravity is 24.8 meter per second square. Then what is the scale height of Jupiter's atmosphere? That is a question. Okay. So what is the equation for scale height? You remember? X is equal to, we discussed this in the last class. Scale height. What is scale height? Do you remember? Or just the equation is also. What is the equation for scale height? Last class we have been discussing. So the equation for the scale height of the atmosphere is RT by G. And again, can you tell me the value of R? What will be the value of R? So here we are dealing with Jupiter's atmosphere. Yes, exactly. Thank you. So the value of R is 8.314. Okay. So R, yeah. So so let this be R star, okay? So the value of R is 8.314. From the value of R, how can we calculate the value of R star? Can you tell me? R star is R by something. So in case of Earth, we know the value of R star is 287 joule Kelvin inverse kilogram inverse. So in order to substitute in this equation, the unit of R star should be joule Kelvin inverse kilogram inverse. The unit of 8.314 is joule Kelvin inverse mole inverse. Now from the value of R, we can calculate the value of R star. How can we do that? R by something. What was that? Remember? It is R by. So in case of the Earth's atmosphere, we know the value of R star as 8.314 divided by the molecular mass of dry air actually. We calculated the molecular mass of air, right? So that's how we found the value of R star. Now in this case, we know the value of R. Now we have to divide the value of R by something to get R star. That's just having a unit of joule, Kelvin inverse kilogram. How do you find R star? How can we find out R star? R by, how did we get the value 287? Yes, exactly. So in this case, what it will be? What will be the molecular value of molecular mass? Yes, exactly. So here in this case, in order to get R star, you have to divide R by 2.22 gram per. So this is the unit of R is joule, Kelvin inverse, mole inverse, right? So this mole and mole will go and we will get the value 8 point. You can find the value of R star actually. 8.314 divided by 2.1, 2.22. How much it will be? Yeah. So in case of Jupiter, yeah, the value will be 3.745. 3.745 joule Kelvin inverse gram inverse. So if we want it in kilogram inverse, we will have to multiply it by 10 raised to minus 3. 3.745 into 10 raised to minus 3 joule Kelvin inverse kilogram inverse. Sorry? Yeah, kg inverse. Okay, it will be 10 raised to 3. Yeah, yeah. So it will be 3.745 into 10 raised to 3 joule Kelvin inverse kilogram inverse. Now, yeah, now can you calculate the value of H from R star that we just calculated? So H will be 3.745 into 10 raised to 3 into T. Temperature is given as 165 divided by G. G is 24.8 meter per second square. What will be the value? 3.745 into 10 raised to 3 into 165 divided by 24 point. How much it will be? How much meter or how much kilometer? Yes, 24,916 meter or approximately 25 kilometers. The answer will be 25 kilometers. Okay. Now, if the scale height is constant, atmospheric pressure increases exponentially with altitude. Is that correct? How about the generally the atmospheric pressure decreases exponentially with altitude. So if the scale height is constant, does will the atmosphere pressure increase exponentially with altitude? Is it correct or false? Is it right or false? At a particular given scale height, does the atmospheric pressure increases exponentially with altitude? True or false? Yeah, it is false. Pressure generally decreases with altitude. At a given um, scale height, the pressure decreases with altitude. It never increases. So false is the answer. Yes. So which of the following statements is untrue for a stable atmosphere? So the atmosphere is stable. When we were talking about the stratosphere and everything, I told you when stability is there, there will be enough amount of turbulent mixing. There will be convection will be taking place. So there will be vertical transport of air passes. So all these things will happen. So if we suppose we are considering a stable atmosphere, which of the following is untrue? So, yeah, which is untrue? Can you tell me? So in the troposphere, we have like troposphere is like unstable kind of atmosphere. Suppose if we have a profile like the stratosphere. Yes. So suppose the atmosphere is unstable, there won't be like cloud formation and precipitation events won't happen in the atmosphere because it will be the air passes won't, the vertical motion will not happen within the atmosphere. So now currently the global mean atmospheric temperature at the surface is approximately 59 degree Fahrenheit. Is this correct or so we know like in Celsius the atmospheric temperature is around 15 degrees Celsius, right? In terms of Celsius, it is 15 degrees Celsius. Now, if we convert 15 degrees Celsius to Fahrenheit, it is basically degree Fahrenheit is equal to degree Celsius into 9 by 5 plus 30. So it will be 15 into 9 by 5 plus 30. How much it will be? Yes, the 59 degree Fahrenheit. It will be 59 degree Fahrenheit. Correct? So the answer is now how many more questions are there? I think we will two more questions and we will wind up. The total mass present per unit area in a car. Is this visible actually? Are you able to read the question? Okay. Thank you. So yeah, the total mass present per unit area in a column of air between the surface and 250 hectopascal is dash kilogram per meter we need to find the mass per unit area in a column of air between surface and 250 hectopascal height. So we have surface and this is the 250 hectopascal height. Now we need to find the mass per unit area of the atmospheric column. Suppose the base area is 1 meter square. What is the mass of this particular column? That's what we need to find. So if you guys remember, last class we actually found the mass of, if we are considering the whole atmospheric column, what is the mass of the atmosphere? We actually calculated in the last class. So here, instead of considering the whole atmospheric column, we are considering an atmospheric column from the surface to 250 hectopascal height, correct? So do you remember from where did we start actually? So to get mass, from where did we start? So we will start from the basic definition that we know, which is mass density is equal to mass by volume, or mass is equal to density into volume, correct? So let mass be dm, just like that, per unit area the mass, and density will be rho into dp. Volume we are considering of this particular atmospheric column. Suppose this atmospheric column is having a height of d set, and the base area into height gives you the volume. It is given that we need to find the mass per unit area, which means the base area will be 1 meter per square. So we can write rho d set. So the mass is basically rho d set. So if you remember the hydrostatic equation that we learned in the last class, it is given by dp by dz is equal to minus rho. So from this we can find what is the value of rho d set, which is dp by g is equal to minus rho d set, correct? So we know dp. So dp, let it be pz minus p0. The pressure at the height z minus surface pressure by g we already know. Is equal to minus rho d z, right? So pz is basically minus of so we can write dm is equal to rho dz is equal to minus of P set minus P0 by G. What is the value of P set which is given in the question? Can you tell me what is the value of Pz? At what height? What is the height of the atmospheric column that is given in the question? Can you tell me what is the value of Pz? Yes, 250 hectopascal. And what will be P0? Surface pressure. Like, it is not given in the question, but that value we already know, right? As Bashwazat said, Pz is already given in the question, which is 250 hectopascal, which is 250 into 10 raised to 2. And surface pressure we already know, just 1013.25 into 10 raised to 2 divided by G. G is having a value of 9. So the answer will be, what will be the mass? Did you get the answer? What will be the mass of the atmospheric column which is extending from the surface to a height of 250 hectopascal? 77.8. Can you tell me the unit also? What will be the unit? 77.8. Can you just have a look at it again? You have to convert the pressure values from hectopascal to SI unit. So, no, check again. The pressure values needs to be converted from Pascal, hectopascal to Pascal. Because Pascal is the SI unit. So 250 hectopascal is 250 into 10 raised to 2 Pascal. So what will be the value? After converting hectopascal to Pascal, what will be the final answer? Is this correct? 77.8 kilogram per meter square. Can you just check again after doing the proper unit conversions? It will be minus of minus 763 into 10 raised to 2 divided by 9.8, which will be 7785 kilo. Yes. So this is the answer, 7785 kilogram per meter. Okay. Now last question. The increase in temperature with altitude in the thermosphere is due to the absorption of UV radiation by ozone. Is it true or false? The ozone molecules are actually absorbing the UV radiation, and this is the reason for the increase in temperature in the thermosphere. That, yeah, it is false. The thermosphere, as we reach the thermosphere, the atmospheric molecules becomes very much rare, and there the phenomenon such as photo dissociation and photo ionization takes place in the presence of sunlight. And because of that, the temperature increases over that region. This thing, like the absorption of UV radiation by ozone, actually takes place in the stratosphere. So this is the reason for the increase in temperature with altitude in the stratosphere, not the thermosphere. So this is false. I think we will stop here for today. We will continue in the next class. Okay. Thank you. Thank you so much for attending and being interactive. Yeah. Thank you, Ritu. Thank you. Bye.